So I moved to the computer lab, and it's kind of dark in here, and I had to rearrange some stuff, but at least the audio works. So I don't know if I want to stay here or not. I got to find a room that I can set up in and just leave my camera set up. So hopefully this will do us for today. But anyway, let's kind of just step back. And if you haven't sent me a text, go ahead and do that now. Send me a text of 513-494-6162. Make sure you put in the text logic control, first and last name. And go ahead and do that now. And I'll erase this in just a second. And I want to talk just kind of briefly about what we talked about in the last class, because that was pretty important. So go ahead and send me the text. So as you know from discussions we've had already, any type of data, any type of information you put into a digital device, which is called a computer, any kind of digital device, we'll call it a computer. Any kind of information or data you put into a computer goes in what we call machine language. And so machine language is just another word for binary. And when I'm dealing with binary, let me just put machine language. Machine language. So if I have binary, I can either have a binary number, which is what we talked about in the last class, or I can have a binary code, which we haven't talked about. We'll talk about that on Friday. But basically, a binary number has what we call place value. But remember we said in digital systems, we don't call it place value. We call it weights. Same thing. Each place has a weight. And the way it worked, what I showed you in the last class, is that just like in the base 10 system, you have place value, you have the ones, the tens, the hundreds, so forth. Well, in base 2 or binary, we deal with binary numbers. You have the same thing. You have what we did. We wrote it as an exponent. We showed an exponential form, because if I do it that way, then the exponent becomes the bit position. That's going to end up being very useful in what we're going to do here. So knowing that this is a 0 position first and so forth. So this is 2 to the 0, to the first, to the second, to the third. And from that, you get what we call 8421 code. So if I just have like 4 bits here, 2 to the 0 is a 1, 2 to the first is a 2, a 4, a 8, 16, 32, and so forth. So I got this 8421 code, and with that, I'm able to figure out, this works with numbers now, I'm able to figure out if I have a decimal number, what would that look like in binary? Or if I have a certain binary number, what would that look like in decimal? So like if I had, I think I gave something like a 1001. Well, the first thing we got to understand is, like, since we're dealing with multiple number systems now, I can't just write this series of digits on the board. I got to express what base the numbers are in. Now, and here it's understood that this is binary. But if you just walked into the room and you looked at the board and you saw 1001, you don't know if that's the binary number 1001 or if that's the decimal number 1001. So I got to show that. So that I would show that by showing a little subscript there of a 2 if it's base 2 binary, or 10 if it's base 10 decimal. But given that this is binary, I can use this 8421 code to translate the binary 1001 base 2 to decimal by saying, I got one of these, I got an 8, I don't have a 4, I don't have a 2, I do have a 1. So a 1 or 8 and a 1, that's a 9. That's a 9 in our number system. So on your calculator, when you enter a 9, on your microwave, when you program it, you enter the 9, what goes into the registers and I just shook my camera loose, hold on. What goes into the memory is 1001. And again, I'll say this one last time. Remember, this is kind of an abstraction from what really goes on. really what's stored in either capacitors or registers or a solid state device is the presence or absence of a voltage. If I want to move these bits, I do that with the waveform. So you want to be able to use this 8421 code to easily go from binary to decimal or vice versa. Today, what I want to do is I want to take a look at binary arithmetic. And you don't really have to know how to do binary arithmetic to work with PLCs or really any kind of digital device. It's just kind of nice to know what the integrated circuit, all of this stuff is designed and implemented through what we call integrated circuits. It's kind of nice to know what the logic circuits are doing. So today's lecture is just kind of for information, although you will be quizzed and tested over the information. So we can do all this kind of stuff. We can convert binary to decimal and vice versa. I can do binary arithmetic. I can do all of that with binary numbers. What about codes? Well, codes we'll talk about on Friday, but basically a code, if I want to represent analog or any kind of information as a code, I just use a sequence of bits. So I can have one sequence to represent a piece of data, and I can alternate the bits some kind of way to represent another piece of data. So we'll get into that in the next class. But today, we want to talk about binary arithmetic, and we're only going to look at addition, subtraction, multiplication. Division is really not that easy. I mean, not that easy. It's not that difficult. It's pretty easy, but I think you'll get the gist of it. If you want to go into division, I don't mind showing you how to do it. Maybe on Friday or something. If somebody asks, I'll show you. But and the other thing you can do is, what if you have a decimal number, maybe 3.5? How do you represent? Number one, how would you represent a decimal point? Because remember, in machine language, there's no way to represent anything other than a 1 or a 0. So you saw that when we looked at negative numbers in the last class. There's no way to, like, if I want to show a positive, 5 or negative 5, well, I can represent this as a series of bits, but how do I represent a positive sign or a negative sign? Well, there's no way to do it. So the solution was we can use what's called a sign bit. So we talked about sign bits in the last class. You can use what's known as the ones complement or the twos complement. You can use these different ways or these different methods to represent sign numbers. Well, you can also do the same thing with a decimal point. You can have a decimal point represented digitally, or if you have a decimal number like a 3.5. So I can extend this to include decimals if I want to. I'm not going to do it. Now, if somebody's interested in it, maybe off camera or something, if we have time, I don't mind exploring that with you, but we're going to just keep it simple in here, and I want you to know enough of this stuff to be able to use your PLC proficiently. So today we're going to talk about binary addition, binary subtraction, binary multiplication, binary arithmetic, and what I have on the board right now is I have a list of the rules for binary addition. So I do have a PowerPoint prepared, and I could just click through the PowerPoint. But I think this works best if you guys don't look at your PowerPoint. I mean, don't even look at the PowerPoint. Just take a second, go ahead and get a sheet of paper and a pen or pencil and get, write the rules down. And what I'm going to do is we'll put some problems on the board. It's the same thing as in the PowerPoint. So don't cheat and look at the PowerPoint. I just want you to just kind of think through the problems. And once you do one or two of these, you'll see it's pretty simple. I mean, I taught over a summer program at UC. I taught some 7th graders how to do this stuff. So it's pretty simple. I mean, it's not rocket science, but what's interesting is that all of this stuff is done with the basic and or not logic, even the arithmetic. It's all done with logic circuits. So maybe we can talk about that later. But anyway, get a sheet of paper, get a pen or a pencil, write these rules down. And what I've done is I've made a printout of some of the pages of the PowerPoint I want to go over. And I'm just going to put some example problems on the board. I'll give you a second to do the problems, and then we'll just kind of work through them together. So if you do it that way, I think it's good practice, and then you'll see what's going on. And I think one of the homeworks deals with this stuff. So go ahead and take time, get a pen, pencil, paper, and while you're doing that, let's discuss these rules. So these are the rules for, and I'm not showing the little subscripts here. So this is binary. So these are binary numbers. And in binary addition, works just like base 10 addition. If I have a binary 0 and a binary 0, the result I get is a binary 0. If I have a binary 1 and I add a binary 0 to it, again, the result I get, just like in base 10, I get a binary 1. If I have a binary 0 and I add a binary 1 to that 0, of course, I get a binary 1. But here you got to be careful. You know, in base 10, a 1 plus a 1 is a 2. Well, in binary, a 1 plus a 1 is a 0, and you got to carry 1. That's base 2. So that's not a number 10, that's a number 10. So if you go to your 8421 code, you put this 10 down here. I have a 1 and a 0. I have one of these. I don't have any of these. So a binary 10 is 2 in our number system. So when you do that, we think of this as a carry. We call that the carry when I write it over one column. Okay, so those are the rules. As you can see, they're pretty simple. So what I want you to do, don't look at the PowerPoint. Just kind of watch what I'm doing on the board. I'll put the problem on the board. You do it on your paper, and then we'll talk about it. So the first one I have in the PowerPoint, I just printed these pages out. Okay, so the first one I have is this. I got a 1, 0, 1 base 2, and I have a 1, 0 base 2. And I'm going to add these and apply those rules to it. So before you add it, though, what is this number? I think you guys can talk to me now. What is this number? What is this number right here? What is that number in decimal?
Would it be 5?
Yeah, so this is a 5. What's this number in decimal?
That's just a 2.
Yeah, we just did it. It's a 2. So that's a 2. So again, these are base 10. If I add those, then I expect to get a 7 base 10. So go ahead and apply the rules to this real quick. I don't have any room in this room. I had to move my computer over to be able to squeeze in here. So go ahead and apply your rules. And then I'll put a couple on the board and we'll just knock them out really quick. So if you apply the rules, then what you should get, this rule right here, if I have a 1 and a 0, well, 1 and a 0, that's a 1. So 1 and a 0 is a 1. A 0 and a 1 is a 1. And I just bring down that 1. So I got a 1, 1, 1, base 2. If you use your 8421 code, you got a 4, that's a 2, and that's a 1. You add them up, you do it, you get 7. So it works out. So that's kind of an example of how it works. So I'm going to put a couple problems on the board, and you guys just go ahead and do them all, and then we'll talk about them. We'll talk about them one by one. So the first one is a 1, 0, 1, 0. I'm going to add to it a 1, 1. So do that one. And then I have 1, 1, 0, 1, 0, 1, 1, 0, 0. And again, it's understood these are base 2. I'm not going to write the little 2. I skipped one. Oh, no, I didn't. Okay, so I got that one. I got that one. So let's try those. See what you can do with those. While you're doing those, I'm going to put the rules for subtraction on the board. So what number is this?
$13.
I mean, what number is that right there?
Oh, my bad.
That's an 8, right? Remember your code. Let's put that up there. I don't know if this orange is showing up in the camera or not. Let me put something darker up there. I don't want to do everything in black. Let me see if the blue works. So it's handy if you just kind of have this up here, especially if you have large things bigger than 4 bits. So I got an 8, I got a 2, so that's a 10, base 10. And I got a 2 and a 1, that's a 3. So whoever said 13, you're right. That should be 13 when I add it up. So if you add this up, you got a 0 and a 1. That's a 1. Now be careful here. Here's how this works. It works just like base 10 arithmetic. You got to carry. So if I have a 1 and a 1, we said a 1 and a 1 was a 0, and that other one we call it a carry bit. So you carry it over to the next column. So the way you think about it is, you say I have a 1 and a 1, that's a 0, and you carry 1, like that. And then you say, all right, if I add the carry to that 0, I got a 1 and a 0, I got a 1, and that 1 I just bring down. So I got that's an 8, that's a 4, that's 12, that's a 1, that's 13. So 13 in base 10 looks like that in binary, and the addition worked. And then the same thing here. I can add, I'm gonna try the green, guys. If it doesn't show up, let me know. I have a 0 and a 0, that's a 0. I have a 1 and a 0, that's a 1. I have a 0 and a 1, that's a 1. I have a 1 and a 1, that's a 0, carry 1. And I have a 1 and a 1, that's a 0, and I just write the carry like that. So let me see, that was 26 and 12. So this came out to be 26 if you look at it, and this is 12. You add those up, you get 38 base 10. And I think if you do your 8, remember you just double, as you go this way, you double this. So I will have 16, 32, 64. I can extend this if I have a bigger number like this. So pretty easy. I think arithmetic is the easiest one. Addition is the easiest part of arithmetic, is what I meant to say. Does anybody have any questions over addition?
Yeah, so if I've got a section where I carry the 1, and then you end up with a column of 3, so it's a situation, it's like 1 0 1.
Like that?
Yeah, something like that.
Yeah, so you would just go a 1 and a 1 is a 0, carry 1, and then a 0 and a 1 is a 1.
Got it. Okay.
Yep, so, and guys, remember, now on the homework, what do I ask you to do on that homework? Well, what I want you to do, I showed you the calculator. Please look at the calculator, but I want you to do this stuff by hand. So like questions like he just asked, you can kind of work a lot of it out yourself, but use the calculator to check your answers so you can turn in a perfect paper to get 100 points. I mean, I don't mind you using the calculator. I just want you to learn what we're doing. And use the calculator to make sure your answers are correct. And if something doesn't come out right, then when we get on camera, just say, hey, how do you do this problem? And then we'll work it out. It's the best way to learn. Let's look at subtraction. So the rules for subtraction, just like base 10, a binary 0 minus a binary 0 is a 0. A 1 minus a 1 in binary is a 0. A 1 minus a 0 in binary is a 1. Now look at this. This is a 1 0. It's not a 10. It's a 1 0, which is a binary 2. So a binary 2, if I take 1 from a binary 2, I still have a binary 1 left. So a 1 0 minus 1 is a 1. So let me give you the practice problems from the PowerPoint. So the very first one, I have this. I got a 1, 1, and a 0, 1, both base 2. And I'm subtracting those. So go ahead and do that one. Then I'll put them all on the board, and we can see what we got. See what you get with that one. What the heck did I do? Oh. It's like 1, 2, 3, 4. 20 computers in here, and the 21 and a printer, and they're all on, and it's like really hot in this class because all the computers are on. I think I'm gonna try to go to a newer building. If I'm subtracting this, well, first of all, what is this? This is let me use a different color. Try to use the colors for emphasis. So this is a
3.
This is a 3, and this is a what?
1.
So 1. So when I do that in base 10, I get a 2. So a 1 minus a 1 is a 0. And a 1 take away 0 is a 1. Of course, that's base 2. So a 1, 0, I subtract it like that. I do get what I do get in base 10 subtraction, so it works out. So let me put a couple practice problems on the board. You work them all out, and we'll compare our answers. So the first one I have is we got a 1, 0, 1, 0, and a 1, 1. Subtract those. The next one I got a 1, 1, 0, 1, 0, and a 1, 1, 0, 0. Subtract those. See what you get when you subtract those. Sure I did it right. 1, 1, 0. No. Okay, I think I'm good. Oh, wait a minute. Guys, hold on a second. I think I picked up the wrong paper. Yep, don't do that. Get it. Wrong ones. I was trying to follow the PowerPoint, but I got so many loose papers in here. Let me do this. I'm just going to put this out of the way so I know I've already done this. So what I should have given you was this. Sorry about that. New room. It's confusing me. So I got this one. This is what's in the PowerPoint. That's kind of what I want to follow so you can see what's going on. And I got this one. Those are the two I want you to do. See what you can do with that. So this was pretty easy. So I go 1 take away 0 is 1. 1 take away 1 is 0. That's a 0, 1 base 2. This is a 2 and a 1 is a 3 in base 10. And a 2 and a 0 is a 2 in base 10. Subtract those. So it works in base 10. It works in binary. It checks out. But over here, see what you can do with this one. Now, this one you got to be careful. You go through it and see what you can do with it, and then if you can't get it, I'll explain it, but I think you can see what's up with it. So with this one, it works like, just like in base 10 subtraction. Let's say I had, I don't know, 721. And I had, I don't know, I was going to subtract 31, like that. If I was going to do that, I was going to subtract that. I say 1 minus 1 is 0. Here I say 2 take away 3. Well, I can't do that. So I can't do it. So what do I need to do? If I come over here, I decrease this by 1, and the 1 that I borrowed, I write that over here. I write that over here. What you got to remember is the 1, since this is in the place that it's in, when I move that 1 over, it comes over as not a 1, but that's a 1, 2, which is a 12. It comes over as a 10. You do exactly the same thing here, same kind of thinking. You got to borrow. So right here, I have a 1 minus a 1. That's a 0. Here I have a 0 take away 1. Well, I can't do that. So I come over here, I borrow 1 from this column. If I borrow 1 from that column, that reduces that down to a 0. But the 1 that I borrowed comes over here, not as a 1, but as a 1, 0. It comes over as a 1, 0 base 2. It comes over as a 2. So now when I subtract, I say I have a 1, 0 minus 1, which is that rule right there. A 1, 0 minus 1 is a 1, and a 0 minus 0 is a 0 base 2. So this is that's a 4 and a 1. That's 5 base 10. This is 3 base 10. I subtract those, I get 2 base 10. There's 2 in base 10. That's equal to 2 if I do it in binary. So that borrowing, the idea you got to borrow 1. Sometimes you got to borrow more than once. I mean, I can borrow 1 from a 1, 0. We do that, you have a 1 left. Let me give you another one of these, because I think I only gave you 2. Let me give you another one to practice that borrowing, and then see how you, actually, I know what I'll do. There's one on here, the next problem. Try this. Try the same thing with this. You have a 1, 1, 0, 0 base 2, and a 1, 0, 1, 1 base 2. So try that. You got to borrow a couple times on that one. If you can do that one, and any one I give you on homework or quiz, you'll be able to do it. Okay, so on this one, I got a 0 take away 1. Can't do that. I got to borrow 1 from the next column. Well, I don't have anything over here to borrow. So what I do is I go over to the next one. I'm going to borrow 1 from that third column. So I borrow 1 from here. I reduce that by 1. That goes from a 1 to a 0. And the 1 that I borrow comes over to that second column, not as a 1, but as a 1, 0. It comes over as a 2. And now I have a 1, 0 base 2. I'm going to borrow 1 from that. If I borrow 1 from a 2, I still have 1 left behind, and I can move that next one over. So borrow 1 from that, reduce that to a 0. The one I borrowed comes over as a 1, 0. And then I'm going to borrow 1 from the 1, 0. If I borrow 1 from the 1, 0, this reduces from a 1, 0 to just a 1. And the 1 that I borrow comes over here. Now this is a 1, 0, and I'm applying that rule again. So a 1, 0, take away 1. 1, 0, take away 1 is a 1. A 1 minus a 1 is a 0. A 0 minus a 0 is a 0. And a 1 minus a 1 is a 0 base 2. So here I had to borrow twice. Let's see what numbers these are. So this is I got an 8 and a 4. That's a 12 in our number system. I got an 8, I got a 2 and a 1. That's an 11 in our number system. 12 take away 11 is a 1. So we people, humans, we do it this way. Computers, machines, digital devices, they do it like this. Now, they actually use a chip called an adder. I'll talk about that towards the end of the PowerPoint. But let's get through this first. Now, I want to show you something else with this problem right here. Let me erase this. So remember when we were talking about signed numbers? So there's 3 ways to represent a signed number. I can use a sign bit. So with a sign bit, I have a number. And if I tell you that number has a sign bit, but if you don't know, if it doesn't use a sign bit, then this bit position right there is your MSB. That's your most significant bit. If I tell you that our digital system is using a sign bit, then your most significant bit is the next one over. That's your MSB. And that right there is your sign bit. That's your SB, your sign bit. If that's a 0, then the rest of this number is the magnitude. So that 0 represents a positive number. If that's a 1, and again, that will be the magnitude of your number, and that 1 says it's a negative number. So we can use a sign bit. Another way to do a negative number in memory is something called the ones complement. With the ones complement, what you do there is you start out with a number like, if I say, all right, take the ones complement of that number, all you do is flip the bits. So this becomes a 0, this becomes a 0, this becomes a 1, this becomes a 1. Anything I'm showing you has to be able to be done or implemented in logic. So if I want to flip bits in logic, the logic function I use to do that is I use the not function. We call it inverter. I invert the bits, and you'll see that. We'll get to that. But I got to be able to implement this with chips. That's all digital devices are these gates, these logic functions that we're working with and talking about. So I got to be able to, the sign bit. Well, that's something that's done or held in memory. One's complement, I can get that by running these individual bits through a NOT circuit or inverter. I can add. Adding is like ORing, and multiplying is like ANDing. I'll show you that later on, but you'll see that everything we're doing here, you can use those 3 basic functions to do any kind of math you want. And the other way is a 2's comp. Now the way you're usually taught to do the 2's complement is you start here, you take the 1's complement, and you add 1 to it. But I don't like that way. It's too much to remember. To me, it's easy to remember. Up to and including the first 1, you keep the bits the same. Up to and including the first 1, you keep the bits the same. So up to and including the first 1, these are going to stay the same. 1, 0, 0. Everything after that, you take the 1's complement of it. You just flip it. So I'm going to flip this. That's a 1. There's a 2's complement. So sign bits are used a lot in digital systems. I think the most used one is that one, the 2's complement. So let me show you what you can do with that 2's complement. Now you got to remember, it's a little weird. The base 2 is a little weird, but these are all representations of negative numbers, negative binary numbers. So let's say, for example, let's say I do this. I have 7, and what I want to do is subtract 4 from it in base 10. These are base 10 numbers. So I have 7 take away 4. If I have 7 take away 4, of course, the answer is going to be 3. But you really can do this subtraction in terms of addition. You really could say, I'm going to take 7, and I'm going to add to it the opposite of this number. I'm going to add to it the opposite of 4. So I'm going to add to it the opposite of a 4 is a -4. So if I add the opposite, I still get the same answer, but I'm doing subtraction in terms of addition. Well, that's how a lot of digital systems do it. They do subtraction in terms of addition. So like this problem right here that we did. If I want to do it like this, well, that's what I did right here. I did it this way. If I want to do a subtraction in terms of addition, if I want to do it like this, then what I would do is this. I say, all right, I got my first number, which is got a 1, 1, 0, 0, base 2. Now this number right here, I got to get the negative of it. So to get the negative of it, I'm going to take the 2's complement. Take the 2's complement. I got a 1, 0, 1, 1, up to and including the first one. I'm going to leave that alone. So that stays a 1. And then I flip the bits after that. That's a 0. That's a 1. That's a 0. So that this is the negative of that. So I'm gonna add the negative. So I'm going to add 0, 1, 0, 1. I'm going to add that now. I'm going to add the negative. So if I add the negative, I have a 0 on the 1. Well, that's a 1. I have a 0 on the 0. That's a 0. Now be careful here. I got a 1 and a 1. That's a 0, carry 1. I have a 1 and a 1. That's a 0, carry 1. So then I bring down the carry. And then you say to yourself, well, but these are not the same. I got 0, 0, 0, 1 here. I got a 1, 0, 0, 1 here. Well, what you do is you always discard the carry. You throw the carry away. So when there's a carry, when you use this 2's complement addition or subtraction or whatever you want to call it, I think in the PowerPoint I call it 2's complement subtraction. When you get a carry bit, you just discard the carry. So I had a 0 here, and I had to carry that. You just throw that away. Now, if you're wondering, well, let me say that at the end. So again, this is on the PowerPoint. I think I use exactly the same numbers. I don't want to run out of time, so I want to go through and get finished with everything and go through the PowerPoint. I got a couple things that's interesting I want to say about this. Take any questions you guys might have. So let's do the last one is multiplication. That is the easiest of all. It's real super, super easy. You just got to remember one thing with multiplication. So multiplication, you have a 0 times 0, 0 times 1, 1 times 0, or 1 times 1. So in binary, a 0 times a 0 is a 0. A 0 times a 1 is a 1. A 1 times a 0 is a 1. And a 1 times a 1 is a 1. I don't know where I learned math. I'm thinking about adding. So, and you guys didn't say anything. A 0 times a 0 is a 0. A 0 times a 1 is a 0. A 1 times a 0 is a 0. And a 1 times a 1 is a 1. The reason I stopped and looked at that like that is because my next thing is I was going to show you, I was going to ask if this looked familiar to anybody. Does this pattern look familiar to anybody? 0, 0, 0, 1. Does that look familiar? Anything we talked about in the past?
I mean, that was the answer that we got when we were doing the 2's complement subtraction.
Think in terms of gates. Remember this? what truth table is this?
That's and, correct?
This is AND logic. AND logic. And so if you look at binary multiplication, it's the same. So what we're going to do, this is down the road. I'm just showing you because it's interesting. What we want to do is we want to be able to do algebra on these binary systems. There's a type of algebra we use called Boolean Algebra. The way it fits in with PLCs is you're going to write logic programs, but you want the program to be as small and as efficient as possible. So you can apply these algebraic techniques to reduce your program down to the simplest, purest program that you could possibly have. And so we got to mimic these things in logic. And so, and I don't want to jump ahead of myself, but you can represent a logic circuit or logic function or program as a truth table. You can represent it as gates, or you can represent it as in the PLC program. But you can also represent it mathematically. And mathematically, this table right here is this. This is an A. Now in your mind, you're thinking dot, but this is A. The dot operator here in Boolean algebra represents and. So that's A and B. But the reason they made it kind of look like you're multiplying is because when you anding in binary is just binary multiplication. That's what it is. So I can use an and circuit when I want to multiply. And that's what they do. They use and circuits or derivations of and circuits. But I'm getting off topic. Let me finish this, and let me just say a few things about this, and then that'll be it. Let's do see where my multiplication problems. I gave you two of them. So one of them is 1, 1, 1 times 1, and I have 1, 1, 1, 1. Times 1, and these are all base 2. So go ahead and do those. And now I'll run through the PowerPoint real quick, and then I'll see if anybody has any questions. Let's go ahead and do the first one. So I got a 2 and a 1, that's a 3 in base 2, and a 1, that's a 1 in base 2. If I multiply 3 times 1, I get 3. So the way I would do this, 1 times 1 is a 1. 1 times 1 is a 1. So a 1, 1 base 2 is a 3 base 10, so that works out. All we did was apply that rule twice. Now with this one, I'm going to give you just another minute to do that one. You got to remember that when you multiply, if you have more than one column you're multiplying, you got to shift it over. You got to shift over 1. So let me give you another minute to do that. If you didn't shift over 1, go ahead and shift over 1, and then you'll see how it's done. Okay, so I have that's a 2 and a 1, that's a 3. That's another 2 and a 1, so that's a 3. So I'm multiplying 3 times 3, and then base 10, that gives me 9. So what I meant by shifting is you'll go 1 times 1 is a 1, 1 times 1 is a 1. But when I come over here, I go 1 times 1. I got to shift over. I got to shift that over, just like you do in base 10 multiplication. So 1 times 1 is the 1 that shifted. 1 times 1 is a 1. And then when I add these up, I'm going to use the purple. This one comes straight down. I get a 1. I got a 1 and a 1. Remember, that's a 0, carry 1. I got a 1 and a 1. Again, that's a 0, and I just bring down the carry. So I got that's an 8 in our 8421 code. That's an 8, and that's a 1. 8 and 1 is a 9, so it checks out. So multiplication is the simplest of all of them, if you remember to shift over. Let me go through the PowerPoint real fast. I'm going to go, we pretty much covered everything in the PowerPoint except for one thing. So I'm going to go through it kind of quickly, and then after class, if you have I'll stick around if you have questions. I don't mind doing that, but I want to get through the PowerPoint just so we're complete. So I'm about to share the PowerPoint with you. We'll go through it quickly, and then that'll be it. Just want to make sure we covered everything. All right, so number systems and code, binary arithmetic. We want to just kind of understand what's going on in a typical digital device. So there's a part of the CPU that does your multiplication. It's called an arithmetic logic unit. Arithmetic ALU, arithmetic logic unit. So every microprocessor has an ALU. And we just kind of wanted to understand what that ALU is doing. So again, we looked at addition, subtraction, where the result is positive, and we looked at multiplication. And at the bottom here, we talk about, I mentioned what I said before, is we actually have chips, circuits, integrated circuits that perform the operations. Now, interestingly, this is one of the things that I wanted to tell you that's interesting. If you think about it, multiplication and division are just quick ways of doing subtraction. Like, so subtraction, let me say it like this. If I want to add, say I want to add 4 plus 4 plus 4. I can add 4 plus 4 plus 4, which I know is 12, or I can say 4 times 3 is 12. So multiplication is a quick way of doing addition. I can do the same thing with subtraction. I can start with 12, and I can subtract 4 from it. If I subtract 4 from 12, I have 8. So that means I have 1 4 in that 12. If I have subtract 4 from 8, I get 4. So that means I have a second 4 in that 12. If I subtract 4 from 4, I get 0. I don't have a remainder. So if I add up how many times 4 went into the 12, there's 3. So in other words, I could have said, well, I'm just going to take 12 divided by 4 and get 3. Basically, division is a quick way of doing subtraction. The reason I'm pointing this out is it's really, really weird, but in your digital device, you really don't need a separate chip to multiply, add, divide. You don't need one for each arithmetic operation. You really only need one that can add and one that can subtract. Because if I want to multiply, even though to us it seems like it's kind of really, it takes a long time. If I had like a whole list of 4, if I had 10 4s to add them up to get 40, remember computers work really fast. So they can add a list of numbers extremely fast. So you really only need a chip to add and subtract. But remember, a few minutes ago, I showed you how to do addition or how to do subtraction in terms of addition. We use 2's complement subtraction. So as long as I can take the 2's complement of a number with circuitry, I don't even need a chip that can subtract. I can do addition, subtraction, multiplication, and division all with one IC chip called an adder. Interesting. So anyway, that's not part of the class, but it's good to think about. These are just examples we've done, so you have the PowerPoints available to you. So these are the examples, the rules and the examples we looked at. These are the exact same ones we did in class. And here's the one on talks about twos complements, binary multiplication. We looked at these two problems. Just remember, and when we multiply, we got to do this shifting thing. And then the only thing I didn't talk about was, well, I did kind of talk about it, but there is a chip called an adder in every digital device that can do arithmetic. There's a part of the CPU called an adder, or arithmetic logic unit. There's an adder in there that can actually do the 4 basic operations: addition, subtraction, multiplication, and division. We only need one chip to do that. So again, it's not important to know this to be able to program a PLC, but it's good to know what's going on inside of the machine. Your simulation software, when you explore it, you'll see it can actually do basic math. It can add, subtract, multiply, and divide, and then you'll look at reasons why you might want to do that in the PLC program. So we'll talk about that. So guys, thank you for hanging in there with me.
Did he leave? I think he left. He might have just joined again.
Can you hear me?
It doesn't join back.
Can you hear me?
There it is.
Yeah, we can hear you.
I clicked off too fast. Let me get rid of this. Because it's like, well, I'll show you what I'm dealing with. I'll turn this camera around so you guys can see. But it's like, I don't know what this computer lab is, but it's like 20, there's 20 computers in here. And it's got the projector. And then it's got this thing. I guess that's the server. I don't know what this thing is. But it's like 100 degrees in this room. I don't know if you can see me sweating. I probably think I'm nervous, but I'm just hot. It's a terrible room, so I don't want to get out of here. Anyway, that's all I have now. Let me see. Do you guys have any questions? I know I had a couple people ask me about the quiz, but before we get to that, anybody have any questions about what we talked about today? Any questions for binary number systems or arithmetic?
Could you go over the twos complement again?
Yeah. So two's complement. What you do is, I'll just make up a number. So I'll make up any string of numbers you want. So if I want to take the two's complement, I start with the least significant bit, and I go over to the first one in the series of bits. So that's this part. You write those as they are. Leave them as they are. So I'm just going to list 1, 0, 0. And then everything after the first one, you flip the bits. So this one becomes a 0. This 0 becomes a 1. It becomes a 1. It becomes a 0, 1, 0, 1, 0. So up to and including the first one, leave those bits alone. Everything after that, you just flip the bits, take the ones complement of it. On YouTube or in your book, if you got the book, it tells you to take the ones complement and add 1 to it. I just think this is so much easier and faster. Does that make sense?
Yeah, that's great. Thanks.
And anybody else? Okay, now somebody, who was it? Was it Luke? Who had a question on the quiz?
Yeah.
Was that Luke? Was that you, Luke?
Yep.
Yeah, man. Why is your audio so low?
I don't know.
Wait a minute, let me see if I can turn it. Okay, Luke, say something.
That's
Luke, why can't I? Where are you? Oh, you're not showing me. Okay. All right, well, go ahead, Luke. I was looking for your picture. You're not. There you go, Luke. Thank you.
Yeah.
So what was your question, Luke?
It was about the last two. I think I was just confused on the last two on the quiz.
Oh, you know what? Let me see if I can. Okay. Let me see if I can bring it.
Comments on the quiz.
Do you know the question?
No, but I can probably pull it up pretty quick.
See if you can pull it up because. Okay, wait a minute. Okay, yeah, you submitted homework too. Send me a text that said that you submitted homework too. When I get home, I'll get it out my email. I don't know which email account you emailed it to, but let me know where you emailed it. If you did, you either email me at my personal email, the UC Cincinnati State. Let me know where you emailed it, and when I see your text when I get home, oh, you said okay, all right. I'll look at my Hotmail account and I'll get it. And yeah, Luke, if you can bring it up, because you know they have that two-factor authentication, and I know you guys probably think I'm crazy. But I do not own a cell phone, so it makes it hard for me to get on these. If I move around, I don't have a way to authenticate myself unless I get into emails and all of that. So if you can pull the questions up, that might be helpful.
Yeah, I got it pulled up.
Okay, which question was that?
It was number 9. If the clock speed of a digital circuit is 2 kilohertz, how long does it take to transfer 64 bits?
Wait a minute. It says the clock frequency is 2 kilohertz.
Yep.
Okay. And what was the other part of the question?
How long does it take to transfer 64 bits serially?
Oh, okay. Okay. So how long?
And then the one after that is just the same thing but parallel.
Oh, okay. I remember.
Yeah.
Okay. So remember when? Let me put this up here. So a frequency 2 kilohertz, and we got 64 bits. Data transfer, serial, and we got parallel. All right, so if you go back to when we talk about the way I'm looking at you on the computer, I guess that looks weird when I look like that, so I'm gonna look at the camera, but I want to look at your face over there. They ought to have that screen in the back of the camera, and then I look like I'm talking to you. But remember when we were talking about data transfer? So if I want to move bits around, I do that using the digital pulse. So there's two kinds of pulses. There's a non-periodic pulse and there's a periodic pulse. So the non-periodic pulse, actually carries the data. The periodic pulse, that's what we mean by the clock. So if a waveform or signal is periodic, what that means is it has two things. It has a frequency, and it has something called a period. But in digital systems, the period is referred to the bit time. So they call the period the bit time. In math or physics, they call that the period, but here they call it the bit time. And we use the bit time to break the non-periodic signal up so I can see how many ones and zeros I'm transferring. So I think when I showed this in class, I showed the clock. The clock is a periodic signal. So it's going to look, it just repeats itself like this. It keeps going. So that's my clock signal. Well, the data signal is non-periodic. So that means, let's say my data, it might start like this, and then go up like this, and go down like that. It might do something like that. That's my data. So I know that this is a positive going pulse, and I know that this is a negative going pulse. If it goes up like this, that's how I show a 1 that's being transferred from one place to another, using what we call a positive going pulse. If I show it like this, that's how we transfer a 0 in the digital system from one place to another with a negative going pulse. And the difference is this started at 0 volts, went up to 5 volts for a certain amount of time, stayed at 5 volts for this amount of time, and then went back to 0. That's how the system knows that's a positive going pulse. Of course, the negative going pulse is the other way around. I got 5 volts. I'm going to drop down to 0 volts for this length of time, stay at 0 volts, and then go back up to 5 volts. When the system sees that, it says, hey, we're moving zeros around. The question is, I can see this is a positive going pulse, so it's representing ones, but how many ones? Well, the way you determine that is using the period of the clock or the bit time. And to get that, you just have to remember the 2 formulas. The frequency is equal to 1 over the period. The period is 1 over the frequency. So this is the one you get to get the bit time. So the first step in doing that problem is figuring out what's the bit time. What's the time for 1 bit? So you told me the frequency was 2 kilohertz. So my bit time or my period is going to be 1 over 2 kilohertz. That's going to give me 0.5, and this will be in, if that was kilohertz, this will be in milliseconds. So the bit time, the time for 1 bit is 0.5 milliseconds. So then you can come up in here and you can just kind of break this up. So this thing starts to repeat right here. That's where it starts to repeat. So like, if I drop these parallel lines down, then that bit time is telling me how much of that low or high is a bit. So like right here, I can drop it down right here and right here. That means that this part of this signal, this much of that, that's one binary 1 that we're moving. And the other part of this signal is another binary 1 that we're moving. And if I keep going, this is a single 0 we're moving. And then this is a single 1 that we're moving. So the bit time divides up the signal. Now to figure out the total time for data transfer, it all depends on how you're sending it. If you're sending it serially, I don't think we need this in. Well, if you got 64 bits over here, I'm just going to make up some bits. I'm not going to draw 64 of them. If you're sending those bits down the wire using this signal, 1 bit at a time, well, each bit takes 0.5 milliseconds to send. So to find the total time in serial data transfer, I'm sending bit by bit, so I got 64 bits times, and each I got 0.5 milliseconds per bit. So I'm going to take 32 milliseconds to send the whole thing. If I send it serially. Parallel data transfer, you're doing like this. Obviously, this machine has some kind of register or some kind of device. It's got to have 64 lines on it. So I got maybe a register. Remember, a register is just a thing that holds bits. It has these cells in it, and it can hold 1s or 0s. So I actually have 64 lines going in. So say this is the 0th one, and this is the 63rd one. And I got 64 lines coming out. And then I got those bits, there's 64 of them, and what's going to happen is, if I load this up with bits, in 1 bit time, all of these things are unloaded. So in 1 bit time, it takes whatever the period of the clock is, and the period of the clock was a half a millisecond. So the key here is just depends on the type of data transfer. Are you sending them in single file, bit by bit by bit, 1 at a time, or if you're doing it as a group? Now on the exam, I'm going to know, all right, well, what's the advantage to do it in one way? And it seems like we want to do it this way. This is faster. It is. It's way faster. It's many times faster. I can move all that data in half a millisecond instead of 32 milliseconds, but this is going to be way more expensive. And it's also going to be way more complex, because whereas with serial data transfer, I can use 1 line, 1 address line. These are called address lines. Here I need 64 of them. And then each address line has other wires connected to it that they use for control purposes. So this is way more complicated. It's faster. It's a trade-off. So typically what they do in digital systems, they use parallel data transfer if there's some device that's going to talk directly to the microprocessor. The microprocessor is so fast, typically inside the CPU, we use this kind of data transfer, parallel. Outside of that, depending on what it is, we use serial data transfer for the most part. Now, USB, I haven't really studied USB. That's universal serial. I don't really know how that works. I don't want to get into that. I need to study that, but that's the essence of that. So that was the first one. Okay.
All right,
I had the same issue.
Okay, so somebody said they put in 0.5 and then what? I'll go in and I'll check that. I'll check it by hand. I'm glad you told me. I didn't realize. That's the only thing about that Canvas system. It's just kind of hard to set that up. I actually changed it because last time I gave a problem like that, I had so many decimal points, and so Canvas had a problem reading the decimal point. So if you put that as an answer, I'll go in and I'll check everybody's by hand, and if you put the right answer in, but the system marked it wrong, I'll give you points for it. So I'll do that by this weekend. Okay, so I'll check that.
I put 1 instead of 0.5 because I thought from the previous problem you didn't want to put decimals. Would I get the point back for that? For the last one?
Who is that talking?
Oh, Logan. It's me.
Logan, can you send me? Don't do it now. Wait till like the weekend. No, wait a minute. Today is only Wednesday, right? Yeah. Send me a text and say, hey, look at this, and I'll go in and I'll look at your. Let me look at the way the problem is worded, and just send me a text of what you want me to do, and I'll look at it when I get inside of there. Just don't forget. Thank you, Logan, for opening up the camera.
Is there any limit?
Question?
Oh, sorry.
Hey, Logan.
Can I ask a quick question?
I was just wondering, who's the ugly dude in the back?
It's not one of my housemates.
I'm just joking. Hey, ugly dude. I'm just joking. Sorry. Does somebody else have a question?
Yeah, I got one.
Okay.
Oh,
Talking.
does resolution apply to both or just analog or just digital?
Ask your question again.
Does analog apply to just digital or just analog?
Does analog apply?
Sorry, does resolution apply to just analog or just digital?
Oh yeah. Oh, okay. Yeah. So yeah, it applies to digital. Just digital.
Okay.
So that's actually a good question. So what does it mean to you? What does resolution mean to you when you say that?
Well,
what did you get out of that discussion?
when I had it written down in my notes, I used both words in the definition, so I put both.
Okay. Yeah, so resolution is, so let me just real quick, I know you might have to go, but let me just say this. So when you have an analog signal, so imagine we had whatever, it doesn't matter. So imagine I had this. I'll just make something simple like that. So there's an analog signal. This is time, and this is, say, voltage, or it doesn't matter what it is. If I want to digitize it, that's the process that we talk about. What I have to do is I got to sample it at regular intervals. So let's say I sample it every whatever these intervals are. So I take a data point right here. I take one right here. I take one right here. I take these data points, and I replace those data points down here. But then to digitize it, what I have to do is each one of these gets a binary number. Now you know what a binary number is. Or it gets a binary code. Typically, it's a binary code. So I'll represent this point right here as maybe a 1, 0, 1, 1, 0, whatever. Each point gets represented as ones and zeros. And the ones and zeros are what I store. The ones and zeros are what I duplicate. So that's the reason why, number one, I can make a copy of a copy of a copy, because I'm basically just reproducing the number. And it's also the reason I can compress it, because I can take a bunch of numbers and I can use an algorithm to kind of just reduce the number of bits I'm using to represent that number. I can compress it. Resolution says, okay, well, I'm throwing away a lot of information right here. I'm throwing away a lot of information. I want to save more of that information. So what I do is I sample it at more regular intervals. So now I got a point here, and I use more data points to represent that. But the more data points I use, the more codes I'm going to have to store the data. That's one disadvantage. The more codes I have to store it, you don't just store data for the sake of storing data. You got to move it around in the digital system. You got to move those zeros and ones, and sometimes you move them as serial. Well, we just had a problem where you saw what the issue was with serial data transfer. So if I have a really high resolution, when I don't need to have a high resolution, then there's an issue. When you work with video game screens or video game cards or a flat screen TV, if you take your television and look, well, you can't really look at it. You have these microscopic, if you have an LED TV, depending on what the technology is, each little light, each little point, I don't know if you can see that, but I'm drawing these little dots. And they use like 3 different colors. I think it's called RBG. They can mix up these colors to get any color, millions of colors to represent basically a little tiny digital speck called a pixel. Well, if I have right here, let's say at 1 inch, if I have 1, 2, 3, 4, 5, 6, I got 6 LEDs per inch. If you stand back far enough from that, that looks like a line. But in that same inch, instead of having 6 LEDs, what if I have 12? If I have 12 LEDs in my television screen in 1 inch, then that picture, when you look at it, that picture is going to look a lot sharper than if it only had 6. You're going to say it has a higher resolution, but really what you're saying, you use more digital codes to store the information in a given length on your screen than you did when you have 6 LEDs per inch. So resolution, depending on if you're talking about video, a higher resolution means a sharper image. If you're talking about music, a higher resolution means a higher fidelity. Some cases you can't hear it, but in a lot of cases you can. So resolution, strictly speaking, means the number of bits I use or the number of times I sample a analog signal in a certain unit of time. But whether we're talking about audio, video, whatever the medium actually is, it deals with sharpness or how clear it sounds, or it just depends on what the quantity is we're talking about. But in general, the higher the resolution, the better. But there's a trade-off to everything. The higher the resolution, costs more, it's slower, so forth. Make sense?
Yep.
Okay, that was a good question. Anybody else?
Yeah, is there any limit to how many bits can be transferred in parallel at a time?
In theory, no, but practically, yes. So I think right now, don't quote me on this, but you know when they talk about they talk about an operating system. So we talked briefly about an operating system, and they'll say that I don't know my versions of Windows off the top of my head, but I know that Windows used to be a 32-bit system, and then there's a 64-bit system. It's always a power of 2 because we're dealing with binary. But what they refer to, what that means is, or partly what that means is the word size. If I have a 64-bit operating system, then I move chunks of that operating systems around 64 bits at a time. And if I do that serially, you can't do it serially with today's programs compared to, like, I got my first computer in 98, I think. Yeah, I got my first computer. Well, the programs that you had in 1998 and the programs that you have like 2020 or 2021, well, the ones you use CAD, you use, I forgot that other one. You know what I'm talking about, though. Those programs are huge. So if you got to bring those up from the hard drive and you do that serially. If you did that in serial, you have to turn your computer load your computer up today and you wouldn't get the program loaded until tomorrow. So a lot of that stuff is they want to move things around in as big as chunks as possible. So I know they have 128-bit operating systems or word sizes, and they can go up from that. The trade-off is there's this, I forget the name of it. You'll know what I'm talking about though. In economics, there's this, what is it? In economics, it's called the point of diminishing returns. I forget, there's a theory in it comes from some economists, but it's the same in engineering. The point of diminishing return remains that you can, if you're doing a calculation, you can get more and more and more accurate, but every time you move over a decimal place, it's harder to get more accurate. And so the point of, at a certain point, it doesn't pay you anymore to be any more accurate. The returns diminish so much, it's not worth your time to be more accurate. Well, it works the same way with when you're designing something in engineering. We can make a 1 million bit word, but then the system becomes so complicated. You got to have a line. 64-bit word means for each register in there, you got to have 64 cells, and each one of those 64 cells has to have its own wire, a physical wire called an address bus, data bus, depending on what we're talking about. 64 lines. So imagine if you had a 512-bit word. You got to have 500 lines. It gets complicated. So eventually, that point of diminishing returns kicks in. You got to say, all right, this is getting way too complicated for the little bit of speed I'm going to gain. It may not be worth it anymore. Find other ways to do it. So in theory, there's no upper limit, but I'm sure there's some practical limit that I don't know about. That's a good question. Who asked that question?
Oh, that was me, Aaron.
Aaron, good question. I should give you guys points for asking good questions.
Oh, nice.
That makes me think. Anybody else have a question? Anybody else? I got Tate, Will, Colin, Luke already asked the questions. Loke, Noah, oh, Noah left. Anybody else have any questions or comments?
Are you a Mac?
Say it again.
Are you a Mac?
Wait a minute, hold on.
Oh.
Am I a Mac?
A Mac or a Windows guy?
I'm laughing because I have a nephew who graduated from, he went to, he was trying to get an ADAPT, but he ended up going to graphic design on Raymond Walters, and then he finished at the Mount. So I didn't know anything about Mac, so I bought a Mac just for him. I bought at the time it was the top of the line Mac. So I bought the Mac, I bought everything Apple for him, and I had I tried to start this company, a digital company. It's called Poppin' Edge Technologies. I'm not going to say any more than that, but this was back in 2004. So we tried to start this business, and so my side of the room had all PC stuff. And I really, though, to be honest with you, I don't know if you ever heard of Unix before, but Unix or Linux, people think it's a language, but that's actually an operating system. So I didn't know anything about Mac and Apple stuff. I always operated on the PC, but I always had a Linux system that I try to get into. I would try to really get into it. But I was in school, and I didn't have time to get into it as much. So I only know Windows stuff. I know very little about Apple's.
There's like Windows ports to look just like Mac OS and stuff.
Say it again.
There's like Linux ports that make it look just like Mac.
Oh, really?
Stuff like,
yeah.
I was just.
I don't know if they had that back then, but
yeah.
I just know. I guess graphics. You probably know graphics people like. They all like. I mean, even here they like. The graphics people love Apple and Mac type stuff, and the engineering people and business people, and they kind of like the PC stuff. I don't know why. I don't know what I guess the graphics maybe at a certain point in time. I'm thinking the graphics must have been way better with the Mac back in the day or something, and it just kind of hung on. So that's my choice. I use PCs. So good question. Okay, well, man, this was fun. I don't get to have fun often. This was actually fun. So, guys, thank you so much for your good questions. And let's see, I'll see you Friday. Monday's a holiday, so we got a 3-day weekend. So I'll see you Friday, and then I'll give you the quiz on Friday, and then I'll see you next week. Logan, have a good day. Thank you, Logan. And then one person had a question. Let me see if I can get back in there. Thank you, guys. See you later.